Um, so for today's agendas, what we are going to do is we're going to do a quick update of the MOCLM progress, and then we know that we have some in-depth discussions about performance optimizations, and we're also going to talk about possible suggestions to the overall roadmaps that are coming up. Okay, so I made a few slides that let me can go and share. Yep, let me see. I can also paste a link to our chat window. Okay, so the first thing is we're going to do a bit of a roundup update on the overall MOCLM progress. I think over the last 1 month, a bit more, we have made tremendous progress. So the first thing that we've been focusing on is the documentation scaffolding. So as of now, we have, thanks to the effort of many here, we have a V1 documentation that focuses on out-of-box binary build, the initial API decoupling. So we'll be able to start work on some APIs that we can build app on top of it, and also tutorials on how we can compile models through MOCLM. So it's still version 1. We're continuing to bring in more improvements overall, but I think it's a decent milestone that starts to help us to getting started from demos and moving on towards some of the things that are more reusable. One of the major themes that we've been focusing on last month and a bit more is we have been working hard on performance and hardware coverage. So the goal here is we want to be able to get these models performant and being able to deploy universally. One of the things that we'll highlight here is there's an initial effort of refactoring some of the performance optimization tools, mainly through a package called dLite, which is now integrated as part of MOCLM. So the goal here is we want to be able to bring out-of-box performance on GPUs. It's a first version, so there's expecting more iterations onwards. But I think it's great to also mention that it helps us to bring a broader model coverage that allows us to be able to pattern match loops and optimize the particular kind of operator of interest. And as a part of that, we have what we call a dLite performance push that help us to getting started from Llama 2 and expand to a broader set of model coverage. So the initial version of the dLite already offers state-of-the-art performance on Apple Silicon and CUDA on particular Llama 7B model. And there's still some room for improvement, as Masa will also talk about from his experience today. But on the other hand, I think it's a great starting point to get a framework of pluggable generic improvements and help us to serve more like a foundational way of deploying better models with universal deployment and better model support. And the goal here is, we want to be able to take in any ML models and be able to run them on a wide variety of environments with out-of-box performance. So I think one of the good things now is that with the new dLite support, we are getting pretty decent Llama coverage. So right now, MOC originally we focused on 7 billion, right? So I think there are some amazing results to be highlighted on 17 billion. So if you have a decent Mac machine that contains enough VRAM, we'll be able to actually run the biggest Llama model out there with pretty decent performance. We also have the iOS chat being updated, Android support coming, which are pretty exciting. And this is the first iteration that helps us to bring universal deployment on the backend, and also some of effort we are going to put on bringing in better model coverage on the front end as well. So I'm going to skip this since this is something that we have to move on in the last part of the meeting. So I think one thing that we could do is we could maybe let Masa first talk about the performance optimization since we touched dLite, and then we can bring up Junlu to talk about the N.module. And finally, we'll discuss the overall roadmaps that that we want to see in the incoming 1 or 2 months in here. Okay, yeah, Masa, please take it away.
I'll share a link to my note slide or note or slide. Okay, so I'll be talking about LLM inference with faster transformer kernel. This kernel, faster transformer kernel. Okay, first of all, what is it? So yeah, so the community has been focused on Delight, which is all about code generation using TVM. But we can also use vendor libraries like cuBLAS or CutLAS to compute Matmore in LLM. So those gem kernels in the optimized libraries operate on the matrix A and B of the same data type. So in LLM inference, we always need to dequantize the weight into float 16 to apply those optimized FP16 gem kernels. And these dequantized steps are significant memory bandwidth. To improve on this, NVIDIA developed a custom gem kernel that directly operates on the quantized B matrix. So it computes this expression in one fused kernel. So in this presentation, I'll call this kernel the faster transformer kernel, or simply the FT kernel. The implementation was originally released as part of the large faster transformer repository, and I'm using the same kernel extracted into a self-contained repo, which is much easier to use. It was very straightforward to integrate this FT kernel into MLC LLM. We need 2 ingredients. One is a new quantization path to prepare weights and scales in the format expected by the FT kernel. Now, after quantization, we use Relax BLC infra to offload a sequence of decode and Matmore into the FT kernel. This integration has been tested on the following models. So I'll be showing the performance of LLM inference using this FT kernel. And I'll be comparing against Delight using the same optimized compilation pipeline I originally developed for the FT kernel, but quantization scheme and Matmore implementation swapped for Delight. Note that Delight is still at an early stage of the development, so it works incredibly well on some models, while not so well on other models. For Vicuna, I'll also show XLLama result, which is one of the fastest open source solution around. Okay, first for Vicuna 7B with int4 quantization, here's the numbers. So for this model, Delight is the fastest, while faster transformer performs roughly equally well to XLLama. This is a bit disappointing, given that faster transformer kernel is much fancier. Faster transformer uses much fancier, given that faster transformer is much fancier implementation compared to Delight and XLLama. Faster transformer uses tensor core under the hood to compute Matmore, while Delight and XLLama uses much simpler matrix vector multiply. So this underwhelming faster transformer result can be understood as follows. So in the decoder, the computation, most of the computation is vector times matrix, also known as GenV. So, but faster transformer kernel always uses tensor core to compute this vector times matrix via Gen kernel. On the Ampere architecture that I tested, oh no, this is not Ampere, but Ampere and also the Ada architecture. The tensor core instruction operates on the matrix A with a tile size of 16 by 8. But since the A matrix is a vector of shape, for example, 1 by 4K, to create a tile of 16 by 8 from 1 by 8, we need to do a lot of zero padding. And so of the 16 rows, only one of the, so 15 out of 16 rows of computation are basically wasted if I use tensor core Matmon. On the other hand, Delight and XLAMA uses simpler vector matrix multiply kernel, so there is no wasted computation. So this is why tensor core based implementation is not necessarily the fastest in the decoder inference. Here I have a operator by operator level profiling result on faster transformer and Delight GenV. So you can see where the performance difference comes from. So for Vicuna int4, Vicuna 7B with int4 quantization, Delight works incredibly well. But for other models or int8 quantization, currently faster transform is the fastest, despite the lot of wasted computation. Here I have results on 7B with int8 quantization and 13B and Dori 12B with both with int4 quantization. Okay, so now that we learned that for a single batch case, faster transformer kernel is not necessarily fast. So then let's look at the batch inference case. In particular, if the batch size is a multiple of 16, then there is no wasted padding or wasted zero padding or computation. So the faster transformer performance is expected to get a lot better. Here I have a result on batch inference on Vicuna 7B. If I increase the batch size by 16x, tokens per second per batch decreases only by 1.5x compared to the Delight batch reinference result, which regresses a lot worse. So I hope that faster transformer kernel is going to be more useful for batch inference case, which is not supported well currently by MLC LLM. I found that the way the KV cache is currently organized makes it necessary to do runtime transpose of the updated batch KV cache. And that hurts end-to-end performance a lot. For example, at the sequence length 128, this transposition takes up the majority of the inference time. These numbers are generated without taking this transpose cost into account. So the generated token will be garbage, of course. So this result should be taken with a grain of salt, but it does illustrate the ideal performance we can expect when this transport problem is resolved in the future. Maybe we can learn from batched inference framework like VLLM to learn how to see how they manage KV cache. Juru?
I have a quick question, Masa. So I was curious about XLLama performance in batched inference setting. Previously we have XLLama performance on single instance inference, which is not as fast as Delight or fast transformer, but do we have any numbers on it in batch setting?
No, I didn't try that. I am aware that XLLama supports batched inference, but I didn't test its performance on batch case. Yeah.
I see. Thanks.
Yeah, but I expect the performance profile will be similar to the scaling behavior will be similar to Delight because they also uses GenV kernel.
I see. And the previous results show that XLLama is slower than Delight in MLC-LLM. Is that
correct? Yeah, correct. Yeah.
I see.
Thanks. Yeah, 4B, yeah, for 7B, yes. Delight is significantly faster, and for even also for 13B, 13B, yeah, XLLama is a bit faster, yeah, but you'll get there. I'm sure you'll get there, yeah.
Okay, thank you very much. I have another question actually. So as you just mentioned, the transposition, which is supposed to be really lightweight, but actually took huge amount of time right now on mainline MLC-LLM in batched inference. Where does this transposition come from? As you mentioned, it's somewhere around KV cache, right? But where exactly does it come from? Is that like appending an ND array into KV cache or take something out of KV cache?
Okay, so it happens after we append KV cache, after we create a new view onto KV cache. And to apply attention, we need to prepare KV tensor in the format B batch sequence length, num head, and head dim. Okay.
I see.
But the KV cache in the KV cache, the sequence length is the outermost axis.
I see.
But we need to somehow, and for batch case, we need to create KV cache per batch.
Right.
Yeah. So currently batching needs to occur at the second dimension, but we need batch.
We're gonna switch it.
At the outermost before abstention. So yeah.
Got it. That makes a lot of sense to me. I think it's something we can really fix it really quick. Thanks a lot for the great explanation.
One solution is simply to implement attention kernel, which can operate on the layout where the sequence length happens at the outermost position. But all the major attention implementation like Cutlass or Flash attention operates on B batch sequence length, num head, and head dim layout.
Right, but Delight has the flexibility to implement attention in any layout, so I wouldn't worry about it a lot. There is some work from Berkeley called VLLM.
Yeah.
Which kind of handles this kind of like KV cache batched inference pretty well.
Yeah.
And we can learn something from it.
Yeah. So that's it about the faster transformer specific performance result. During this development, I also did other optimization for CUDA, which might be of interest. First, combining parallel matmos in QKB projection gives huge improvement of 20 tokens per second if I use faster transformer. Parallel matmos here means a sequence of matmos sharing the same input. Those matmos can be combined into one bigger matmos, which is much more efficient. So this gives a huge speed up. So we should always do this. And interestingly, even so with KV cache, the only dynamism in the decoder is around attention. So we can put MOP after one attention and QKB projection before another attention into a static CUDA graph. And this gives 1 tokens per second improvement consistently. I was hoping that it will be much better, but the improvement is very small. But I think it is interesting that CUDA graph is relevant for LLM inference. For attention, I am using the Cutlass attention kernel with causal mask optimization. But there is a room for improvement in the way we use attention in the decoder network. So after we combine QKB matmore, we end up with split. Split is here for splitting concatenated QKB tensor into 3 pieces, QKB tensors. And we apply rotary embedding on Q and K, update KB cache, and do attention. So, and this split is the overhead which is a consequence of combining matmore. For example, you can see a split here. This happens only because I did matmore combining. But the Cutlass kernel and other implementation can directly operate on concatenated QKB tensor. So in principle, there is no need to split. Our VLC bug infra supports fusing split and attention. But the rotary embedding and KB cache update in the middle prevents fusing split into attention. So we end up with split here. Currently, I manually fuse split and rotary embedding into a single kernel, and that gives about 1 tokens per second improvement. But ideally, I want to fuse all of them, all of those preceding operations before attention into attention in the kernel itself. That's not possible if I use the Cutlass kernel, but there is alternative attention implementation in FASTA transformer, which does support fusing all of them. For example, this kernel takes as input the old KB cache and the new K and V tensor, and does KB cache update it does KB cache update inside the kernel that also does attention computation itself. Moreover, this attention implementation is specialized for single query attention in the decoder network. So it uses matrix times vector multiply kernel rather than tensor core matmore in attention, which is, and we learned that for single query case, tensor core based matmore is not faster than matrix times vector kernel. So I expect that this decoder specialized attention is faster than the Cutlass attention kernel that I'm using, even without exploiting this fusion capability. So I'm going to integrate this kernel into a pipeline and see how much performance can improve. Yep, that's it. Thank you for listening. Questions?
This is great, Masa. I really love the performance benefit that you bring to MLC-LLM, making it really running really fast. I was wondering a couple of questions. First, so for split rotary embedding fusion, so the split operation only does memory copy, which can be unnecessary if we directly like fuse this operation or say remove this operation if split happens on the first dimension of any vector, any tensor. Is my understanding correct?
But this split after combining, this split happens along the rows, on the columns of the concatenated weight, the concatenated tensor. So, but even for even if we are splitting along the first axis, we do need a explicit copy, isn't it?
If it is the outermost dimension and the input tensor is not used after,
Okay, yeah.
I mean, if we transpose the inputs of split carefully, and it is possible to kind of remove it. But the biggest challenge here is how do we? I wonder how do you fuse rotary embedding into like matrix modification or batch the GEMV?
Oh no, we simply by fusing rotary embedding into attention, I simply mean that inside attention kernel, when we load K and V tensor, we just do rotary embedding before doing any matmore.
Oh, I see.
This kernel also takes as input the sine and cosine vectors that's needed for rotary embedding.
I see. That makes a lot of sense. Okay, this is awesome. Thank you very much for sharing, Masa.
Yeah.
Thank you, Masa. Great talk, and it's really looking forward to see more iterations, and it's great that we start to do a bit more learnings of where the performance coming from. And so now we have covered the performance part. I think moving next, we're going to cover a bit more usability. So let's hand over to Junlu to talk about the new module proposal. Yeah.
Give me a second. Thank you. Thank you, Masa, for the great talk, and thank you, Tianqi, for the introduction. So today I'm gonna talk about. Let me find out my slides first. Today I'm gonna talk about the new usability improvement in MLC-LLM as a whole architecture to define neural networks. We temporarily name it as n.module, which is a little bit too general until I find a better name. Anyways, never mind. So the problem as of today, if we take a closer look at MLC-LLM REPL, for example, how it defines a llama architecture, we'll find out that it took close to 1,000 lines of code to define an architecture. And if we sell MLC-LLM as a whole box, it's probably fine. People don't care about how difficult it is to define an architecture as long as it is exposed on useful APIs. But there are more needs to get into the architecture and slightly modify it. There are a couple of examples. For example, let me see. If we wanted to get an embedding vector to be used to be integrated with, say, LangChain or other vector databases, or if we wanted to customize its embedding from rope to like extended NTK or other embeddings, it will require some knowledge about how to define the neural net architecture and how to change it. As opposed to this complicated, if we look into a complicated API, we'll see it is actually using multiple layers of TVM, which includes Relax TE, relax.testing.nn, Relax TVM scripts, and many and TLR, many which requires extensive knowledge about TVM, which is not actually super friendly to people who are not working in MLC world. And to make things even worse, if we wanted to make sure that our implementation is correct, we gotta fix the inputs and compare the outputs in between MLC's Llama and say PyTorch's Llama or Hugging Face's Llama. And the comparison, the debugging logic there requires like 200 lines of boilerplate code. It was super tedious and error prone and really hard to write. So motivation of this project is we want to make things really easy for developers. Our goal of this project is, first of all, we wanted to make it really easy to build neural networks. We wanted identical API to PyTorch so that any any PyTorch users, if they know PyTorch already, they don't have to learn anything new. They just use the API to build the neural network they like. That is the first thing. And second thing, to seamlessly integrate with PyTorch and debug with it. So say if we implement an attention module and we're not sure if it is correct, we just write an attention in PyTorch and compare the input and output, torch in, torch out module that can be used together to debug with PyTorch. And third thing is we wanted the API to be really isolated, and developers don't have to learn anything about TVM to define neural networks. So that say next time Falcon, MPT, and other architectures are out, we can any developer who is interested, they don't have to learn anything new about TVM or MLC. They just write it in like PyTorch syntax and just get it work. Okay, so there are 4 design elements in this project. And the first 3 are user-facing classes, and the next is not. First is tensor. Tensor is something we all know. It is n-dimensional array, which has shapes and d-types. Implementation is backed by relax.expression with tensor struct info, but this is not important to external developers. We just know it is a tensor. It is the same tensor as PyTorch tensor, TensorFlow's tensor. Yeah, this is, I would say it is not a new concept. It's just a tensor, but it supports dynamic shape anyways. And a parameter is a subset of tensor. It is a concept that exists in PyTorch as well. Say a parameter can be a weight of neural network, bias on neural network, anything else like embedding or something. It can be bound to any concrete value, say some concrete value, say NumPy is ND array or PyTorch tensor, and it can be collected by module.named parameters. A parameter that can be, of course, be quantized, in 4 quantized or in 3 quantized to the format we want to deploy, like the faster transformer format that Masa just mentioned. It is fine. It is decoupled with the system. And module is also a concept that already exists in PyTorch. It is something, it forms a tree structure to define whatever neural network architecture it is. Okay, and the effect is something that is hidden from users. They don't have to learn what is a side effect in programming language, but it's used to define, say, runtime, like printing some contents of a runtime behavior, like printing the contents of tensors or doing in-place mutation, or most importantly, KV cache. Okay, so the design of this dot module is that basically you only need to know what is a tensor, what is a parameter, and what is a module, and you can define your network yourself. Let's put it up with a demo here. This is attention in Llama. To define attention has QKVO, QKV projection. It is basically identical API to PyTorch. It's, you declare a linear layer for each projection, including output projection, and also KV cache for key and values. Nothing else. It is pretty succinct. And for the computation in Llama, it is like 20 lines or something. Like we first do QKV projection, and then rotary embedding, and then KV cache manipulation, and then do calculate attention scores, normalize it with softmax, and do output projection. It is noteworthy that it is much simpler than current implementation in MLC LLM, which requires pretty extensive knowledge about like relax.shape tuple get item or n.emit, those pretty opaque APIs or struct info, and just as straightforward as PyTorch. And for KV cache, it supports like extensive operations over it, like replacing the chat history stored somewhere else, as much as user like. And also, if users wanted to get an embedding inside some layer, like the last layer of attention, they can simply return it as an extra parameter when building a neural network without having to do a lot of hacking. Okay, this is a attention demo. And then how does this module interact with TVM? It is actually pretty simple too. Like if we have a model defined in TVM, we just need to specify which method to export. Usually in neural network, there are two major in large language model. There are two major methods, which is prefill and decode, encoding and decoding, and it supports static shape and dynamic shapes. It supports tensor as inputs and integers as inputs. And the output of this export TVM method is a TVM-IR module, which can be further used to compile, to deploy anywhere as long with TVM's APIs. This is the second demo. And the third one is about the torch in, torch out debugging experience. We have a JIT API that you provide the same spec here, and you can specify the output format as torch, and then it is compiled to a torch. Torch is an module, and you can we expose APIs to allow you to say call this prefill methods with torch tensors and like Python integers, and the output is also torch tensors. Imagine you want to confirm the correctness of some module. You can simply like call this method and compare the results from using the same torch inputs. Sure. So to summarize, module is an isolated layer on top of TVM, but by isolated, I mean users do not have to learn anything about TVM, so that they can build neural networks themselves in a very agile way. And we expect to use module to build new to cover more and more architectures, like the ones that we just mentioned, like MPT, Falcon, those kind of things. And also like multi-model neural network architectures like mini GP4, which already exists. We wanted to refactor on top of this, and also like say audio models or like diffusion models as well. Okay, that's it. So any questions?
This is great stuff, Junru. I wonder, actually, since you make such a point of the API matching PyTorch closely, could this also be a solution to our PyTorch importing problem down the line?
Well, I think right now PyTorch, we do have a PyTorch importer which functions in many cases.
Most of the time.
Most of the time, yeah. And I would say it is not going to be a replacement to PyTorch importer, because I wouldn't imagine people wanted to redefine their neural network once again if the PyTorch importer just works.
Yeah.
But for large language model case, the case for large language model is that it requires dynamic shape, which is in theory supported well by TorchDynamo, but in practice there could be graph breaks, which makes it really hard to get an end-to-end compute and deploy that on the phone without PyTorch. So in this case, I would say they are like pretty much complementary to each other. One thing that I think this design, module design, would help PyTorch is that PyTorch naturally has some in-place mutation. For example, in-place copy from one tensor to another tensor, or which is not supported by existing like relay stack, forbidding us to run TorchBench or extensively. The thing that module encloses side effects like implicitly, and converting side effects to making explicit in RelaxIR makes it possible to import those graphs and finally run TorchBench over it.
Sure. Yeah, it's just, if we match the API perfectly, someone could take their PyTorch model, copy paste, do a string replacement, and get one of these NN.modules. That would be lovely. I just the importer, the PyTorch importer we have, it relies on getting JIT traces. That can be tough, but actually using the same API might have some advantages.
I hope so. And one major difference between this API and Torch's API is that Torch is mostly eager execution, which means the value of tensors, the content of tensors, they are evaluated on every line of execution. And the control flow in PyTorch model, they can be they can be determined by runtime value of tensors rather than static computation. And this NN module design doesn't take this into consideration because effectively in modern neural networks, there are effectively no much control flow, no. But I would say if there is control flow, it's going to fail.
Gotcha.
But at least in large language models, in most of the cases, you can just copy paste from Hugging Face and just run it.
Thanks, Junru.
Okay, cool. Any other questions? So the timeline of the project is that we wanted to get it upstreamed, get this foundation upstreamed. Actually put up one PR already, get it upstreamed by the end of this week. And I wanted to put up a design doc with my collaborators, Le Sheng and Yaxin, this week. And I wanted to upstream the Llama implementation, which I have already here to MLC, MML, LLM to actually use it. And then next week, I'm going to upgrade GP Neo X, which backed Red Pajama and other models using this MLC LLM, and then gradually expand the coverage and make it more accessible to other developers. Okay, that's it.
Sounds great. So thanks, Junru, for presenting. So we have last 15 minutes. I think one thing that we are going to do is we're going to quickly go over the roadmaps that we are going to looking at in the next month. So we're also open for suggestions. So one of the things that I think Junru already mentioned is we worked a lot on performance, and we're going to continue working on performance through Delight and hardware coverage. Specifically, I think Android support is a bit lagging, and we are still, but hopefully with the new Delight, we are able to get that coverage back and bring more models. One of the things we are looking at is, more multimodality. So there's an image generation model that's getting close to landing with NDOT module. My hope is that, we will get more kind of these models landing. And also you might have seen there are some tutorials on using MLC through Python API. So if you have any suggestions on ways that you want to use these things, definitely send us feedbacks in here. And of course, the module is something that we're going to working hard on. Yeah, so I don't have any additional agendas, but if anyone want to, so I think what we can do is we can do a bit of open mic, or we can close early and give everybody back 15 minutes. Yeah.
I do have a question. First of all, congratulations. I've been here on the first meeting, and between that meeting and this meeting, I think your community size has grown like almost 10 times. I'm seeing in the Discord there's like over 1,000 users already. And obviously, a lot of the new people coming in are not machine learning engineers like myself. Basically, we are kind of users that will be kind of consuming what you guys are producing. And there's some confusion, and I'm still not too clear on, even after a month of standing by and trying to learn from everybody, about the ability to fine-tune quantized model. Whether that is that part of the training process which happens in like big system Python data center, or is it actually left alone because these kind of like deploy LLMs on small machines are new, and that's kind of a research area. It's just that it's is puzzling to me and also many community members who came in since on why we're not able to use the Swarm machine also to do fine tuning of the models.
Yeah, so I think this is a
okay.
great point. Fine tuning is certainly something that we are working quite hard on right now. So actually, I think first of all, it is possible, right? So it will take a bit more work because there's memory constraints and so on, and also there's a lot more works to optimizing the hardware performance. So a lot of work that we're doing right now, like expanding and making sure that we have hardware performance portability for inference, is going to translate onto some of the fine-tuning effort that we are going to do. So my take is that we're going to see some of fine-tuning results in the incoming, maybe not next month, but in coming 2 months. And in the meantime, MOCM do have ability to be able to deploy any fine-tuned checkpoints that you have right now. So for example, if you have a fine-tuned version of Llama 7B, right, that you want to deploy on any of the environments that or 6 or 17B or any of the environments that we support, this is supported already. So so yes, this is something that I think is definitely interesting, and we're looking a lot into. Yeah.
Okay, that's pretty cool. A second question there is kind of puzzling on how come the Llama 2 model between release and actually you guys coming up with like something is so quick versus some of the other models is taking like a lot of time. What's the difference here?
Okay, that's a great point. So I think it just happens that first of all, over the last months, right, a lot of effort we have been putting on have been go to what we call out of box performance. Actually, getting a model up is not that hard. Like if we put a bit of effort to it, we'll be able to get a model up. But what's difficult is that actually, when you get up, you want to make sure that it runs the state of art on the platform we are interested in. So a lot of effort are on Delight in the last month, so that we get that out-of-box performance. And it just happens that as we planned originally to finish Delight Sprint, and Llama 2 just came out, so it's kind of right fit into the bullseye that we're trying to hit. But moving forward, right? So with the N.dot module that Junlu is bringing in, the ability to ship new models is going to be much faster. So in the last months, we focused on the performance and all about performance, so that get us from originally Llama 7B. Right now, we can support Llama 7B, 13B, and 17B. And I think in the incoming months, likely you are going to see a catching up of model coverage, like recurrent models, different variant models with N.dot module. My hope is that we can get that models bring up time down to a week to a few days even, right? And then also because of our out-of-box performance we have in here, we'll be able to enjoy good performance. So yeah, it's an iterational process that we are going to see more acceleration moving forward in here. I also see Shiva post a question about, are there any plans to bring auto-tuning support for tier dispatches? And this is a great point. So one of the things that we're focusing right now is actually Delight is focusing on, we are trying to first get some kind of like a sketch rule so that we'll be able to get good performance without auto-tuning. The idea is that we want to try to understand the space, right? In a lot of cases, we will be able to write kernels that analyze the loop patterns and trying to get the good performance. But we're also aware that in certain cases it's useful to tune, right? So one of the things that we are thinking about is adding a tunable that we have on the Delight rules, and because it's already integrated as well with the MetaSchedule infrastructure, so hopefully it's going to connect. And if you're interested and have any thoughts on that, do bring up, and I think we'll also love to learn more in there. Yeah, Junlu may have something to say as well. Yeah.
So for Delight, it is designed to be compatible with existing performance auto-tuning infrastructure that is TVM's called MetaSchedule. And right now Delight is focusing a lot on out-of-box performance, as Masa shows in 7B models, were actually much faster than XLLaMA and other existing solutions. But during experiments, we find out something also interesting, that is on different models of GPU cards like 3080 and 4080, the performance might the scheduling, the kernel writing strategy, the same strategy, the same two strategies, they deliver different kind of performance. Like A is better than B on 3080, and B is better than A on 4080. And in those particular cases, and the difference can be like in between like 2% to 10%, even like 20% in cases. And in those cases, auto tuning is a must for us to deliver the optimal performance. And this is something we need to, we have design in mind in the very beginning, and we wanted to expand in the incoming months.
Okay, good to hear that.
Yeah, Shiva, do you want to say something?
No, I'm saying good to hear that you're bringing in auto tuning, because even with Adreno, we see some opportunities of tuning the existing TR dispatches is giving pretty good improvements.
Oh, really? Okay, that's really good to learn. And, you know, we would love to learn about your lessons as well. Actually, Bohan right now is trying to update the D-Lite schedules to be able to support Adreno. So if you have anything that you can share in forum or other ways, we'd love to learn more. And maybe
the baseline is actually only two. I think we try to use better vectorization, and there are more threading possibilities are there for Adreno, specifically on Gen 2.
Okay.
Extended TR schedules are little low. It's not actually using the full capabilities of Adreno.
Okay.
So those changes, I think, yeah, I mean, I can give you some rough figures. I mean, we could do around 9 to 10 tokens.
Nice. So
both Llama V1 as well as both.
Nice. So is it possible for you to share some of the schedules you do with the folks? I mean,
we are actually working on it. We have streaming permissions for the TVM community, but CLLM, I'm working with the legal team to get those things clear. So we are also eager to bring those things, give those things back to the community.
Sounds good. Yeah. And you know, as we start to work on D-Lite schedules, definitely. So effectively, we are seeing that the elements here is better vectorization and threading.
Right. We are doing vectorization of 2 for some of them. I think going for 4 has a better opportunity. And the next thing was, I think we did get in the R factor. We are one vector, one thread is doing nearly 11K number of multiplications.
Okay.
Rather, we can make more 4 threads to do small parts and then do a reduction.
I see. So you're saying that, you know, effectively you are trying to thread over reduction dimension so that you can have better parallelism.
Right. That improves a lot.
I think that.
Yeah. And by the way, the number of the threads that TVM, I think I can send a PR on that. The thread count is limited to 256, but I think Adreno already has moved to 1024.
Okay.
Half per workload threads up to 1024.
I see. Yeah, I think that, you know, if you use 1024 threads, it will be easier because Adreno have moved on to that number of threads.
Yes, I think I remember the target definition is still showing 256, 256. And even local memory it is showing 16 KB, but we now have 32 KB. I
see. Yeah, so you know, one of the things that we are doing is we are trying to put the D-Lite rules in TVM Unity branch, right? So you know, maybe that is a good place for us to collaborate as well on Adreno related things. Cool. Thanks, Shiva. It's great to learn that, you know, we are able to bring things up even further, and looking forward to seeing more results here. Yeah.
Thanks.
Cool. Any more comments? Looks like, you know, we have a lot of interesting things lining up. Yeah. And thank you, folks. And one of the things that I think if we find it helpful, we do want to make a reoccurring meeting. I know that this time, like a lot of people at SMO, so hopefully next time we'll also get more people around, and let's plan for a meeting in the incoming months, and hopefully, you know, we are going to see more updates here. Yeah, cool. Sounds great. Thank you, folks.
Thank you.
See you guys
Thank
next time.
you.
Good to see you all.